对啊，还有比数学老师有学。
大小可以量表都是细致的。
Okay, so we continue. Okay. So let's get ready. Finish this one. Now I continue with another examples of 3D. Okay, drawing another three-dimensional objects. Okay, so you can click on this class 1 again, just to open the 3D perspective. Okay. So the previous one just based on segments and points, right? But you can also start with polyhedrons, right? Something like that. Okay? So these different kinds of polyhedron, including cubes. Cubes is a very common one, okay? And tetrahedron, prisms, and pyramids. So these are also quite common in a lot of math curricula. Okay? So you can have to try. They can be constructed in different ways. For example, a cube, you can create a cube just by choosing 2 points, right? As forming one segment of the cube. Right? So the blue dot here to suggest you or remind you that you just need to choose 2 points in order to create a cube. Right? So you can see the hints there as well. So let's, for example, a cube. You click on the cube. Then you can choose 2 points on the plane. I usually like the point on the axis because it let me know that the cube is center, right, at the origin. It's up to you. Actually, you can choose any 3 points you like. Okay? But I think these 2 points are equally far away from the origin to make it quite nice sitting at the center. All right? Okay. So once you have a cube, then you can select any part of it. For example, this part, okay, you can also choose to change it. Do you know what I'm doing? I'm changing some of the space. Right? Now, because you don't actually see the individual faces here, do you notice that? Right? So a little bit tricky. If they show all the faces, the list will be very long. Okay? But you can still highlight or modify individual faces if you like. Sometimes you just want to see, okay, part of it, just something like that. Is it okay? Or if you like to take this off as well, something like that. Now here, this time, if now you choose to take away the plane, it's still fine because you don't need. Now this time you don't need the plane, perhaps. Okay? You will just, because you have the base, okay? Of course, you can still turn it on if you like. It will be like this. Is that okay? Right? Okay, now maybe I ask you a question. Now you can still make polygon inside it by clicking vertices. Okay? So if you click on this vertex, then you have one triangle. Can you see this? Maybe I can make it a little bit dark so that you can see more clearly. Right? Or maybe still not too good. Is it better now? Okay. And do you know how to make this triangle?
Yes.
G joining the third edge further down. Okay. Opposite it, you can say. Actually, another triangle can be drawn the same way through the point G, connecting A and B. Can you do this? So I can also turn it a little bit darker. Not too effective. Okay, can you see this? Yes. So you can practice drawing different segment faces, okay, in this 3D window. Now there's a lot of things that you can try. Once you have some basic objects, right, just like this a cube or polyhedrons, okay, and you can build on this different parts or segments and surfaces and talk about the relations. Now, for example, do you know the angle between these two triangular faces? Do you know the angle between these two now highlighted triangular faces? 60? How do you know?
Yes.
120, how do you know?
By moving like this.
Ah, yeah, you know some useful tools, right?
Yes.
So if you move it, then you can see the way it's moving.
Oh.
Yeah, you see this? Is it convincing?
No.
Right. Now we can draw the axis. Okay. And it may help a little bit. And remember the wheel in front. Okay. So you can choose the axis, and it will help you to locate it. But is it obvious that the two planes are making an angle 120 degrees? So which is also the same. If you say that it's 60 degrees, it depends on which angle you look at it, right? The acute one or the obtuse one. Well, of course, the common textbook method is not like that. Okay, the common textbook method will require you to draw a perpendicular line to reach the intersection, and then use a cosine formula to find the angle. Okay? There's a long list of calculations, but still you get 120 degrees. You can try, okay, and let's see how you get it. Or you can even add the third plane. It may be more convincing if you add the third triangle here, and then to see how symmetric they should be. You know what I mean? Now I add the third triangle, also from G, okay? And then if you imagine that the three triangles should be more or less the same because they're inside the cube, which is so regular, right? Then they should be symmetric. Am I right? Right? So it can be also another argument. Right? Why the plane should be 120 degrees or 60 degrees. Okay, so just a little bit experiment to try. Now remember, if you want to make a mark the angle, you can use the perpendicular line here again. Perpendicular line from P to the axis, or from this is from P to this axis. In both ways, you can see the line from the vertex, okay, and then meeting the diagonal at the right angle. So if I now select point at intersection, then I can select any two of these in order to mark the intersection. The intersection is now marked. If I turn it off, if I hide it, then perhaps you can see more clearly the intersection. Together with the point joining B and B, perhaps. Usually you look at this triangle, this inside, the triangle inside, to find the angle you want. Okay. So you can finish the step yourself. Okay. Or you take away the base. I don't know whether it's better or not if you take away the base. And that is the angle you have to check. Do you see that? So angle DID. DID. Okay, now we can measure it. Angle DI and then D. Right, so it's 120 degrees. actually look at it this way. So because I marked the intersection, then I can measure this angle. So I think you now know a little bit more how to handle the 3D objects like this. Right? So this is another one I can save. Right, can I do another one? So I close this one and then let's see. Now perhaps now I turn to the trigonometry, okay, examples, which also show you the use of more than one graphic views. Okay, so I still use the classic window. Can you see this? Now, so by default, you see only one graphic window. Okay, you can choose the axis and the grid. Can you see this? Okay, and so you can also enlarge it. I like to start with a unit circle. Okay. So there are many ways to draw a circle. Okay. So the common way would be just a center, circle at center, and through a point. Okay. So maybe I can take it as, because I just want a unit circle. Okay. So I click here. But of course, if you really want B to be really 1, 0, then you can input directly the coordinates. Okay? Otherwise, the point B is still moving. Okay, can you get it? Yeah. Now then, just like the previous example, I can start with an angle. Okay? For example, I can create a slider to make a variable angles. Okay? It may be easier for the following demonstration. Right? So the angle, you can call it alpha using the Greek alphabet or any other letters you like, okay? Or the ordinary letters. Right? Even theta, but theta may be more complicated because it can be used as another default variable, right, for polar coordinate functions. Right? That's why sometimes you may avoid this angle. Okay, it can be from 0 and 360 degrees or any other range you choose. Right? And then increase by 1 degree. Right? So it could be very nice. I think with this interval. Can you get it? Yeah. So I have an angle, okay? And I can put a point based on this angle on the unit circle. Just input coordinate. Do you see I input the expressions here in the algebra view? Okay? So this is the area for you to input directly any other objects you like. So I like the coordinate cosine alpha. Okay? So you may need the keyboard again to input this, and then continue. Can you get it? Okay. So you can press enter. Then I have a point C. Can you see the point on the circle? So it may help you to do some exploration or demonstration of the unit circle. Can you get this? This is a unit circle, as I emphasized, right? So the radius is 1. That's why I put the coordinate directly here in this way on the circle. Oh. And in fact, I like to use it to demonstrate the basic definition of trigonometry in unit circle. Right? So because the cosine and sine already directly describe the coordinates of the point on the unit circle. Okay? And based on exactly alpha, in case you want to demonstrate alpha, I mean to show it geometrically, you can go on to use the mark angle tool again. And it's quite simple, just like the previous demonstration. Right? Or add the segment if you like. Can you get it? Now you have a new angle because the name of this angle is beta, but the size is the same as alpha. Okay? And you can change the label because you may not want to confuse the two. So you can hide the name but just show the value. Then it looks like that exactly the same angle actually, 60 degrees. Can you see this? Is it okay? Well, there's other simple things you can play with this drawing. Right? Now I hide the angle, I hide the segment as well. Where's the angle? Maybe I should set again by object type so that I can find the objects easily. Right? So the beta, I don't need it now. I just close it. Okay? Can you see this? All right, so I have basically 3 points, A, B to start with, and then the C, a variable point on that. Okay, I add another point. As I mentioned, you can use it to describe the basic definition of trigonometry, right? So if I modify the coordinate, then you can talk about it. Where would be the new point? Let's say if I like cosine alpha plus 30 degrees. Degree can be found, the degree symbol can be found here, and the keyboard. You press F of X, then you see the function symbol together with this degree symbol, all right? So you can have this. Because you can go on to talk about the basic definition of trigonometry, okay? Now you can guess where should be this one. Cosine alpha plus 30 degrees, sine alpha plus 30 degrees. Right? So you can try to locate it somewhere on the circle, and then enter it. You have the point D. Right? Now you can modify. So you can modify the angle. If it's not 30 but 60, then what should it be? So this will give you the idea how the coordinate is represented, right, by the trigo functions. Okay. And based on this, now you can make a simple graphic pattern. If I connect it by the segment. Remember the trace function? Can you remember? Right, so I can use the trace function.
Wow.
X.
Okay? So do something like that. Yeah. So I'm not doing multiple segments, right? I'm just trace the segment. If you enlarge, if you modify the wheel, then the trace will be removed. Okay. At the same time, I hide the segment, right? So that you won't see the trace again. Because I would like to try another demonstration. So you can invite the student to make a guess. What would it look like? For example, if this coordinate is now, what other things you want to try? Cosine alpha with 60 degrees.
180? No,
180, you can try,
yeah,
but the pattern may not be so interesting. How about 2 alpha? What would it look like? Can you see my point here? Can you see the point? Right. Can you talk about the relation between the 2 points? This is cosine 2 alpha, sine 2 alpha. Okay? And then you now, okay, let's go on to turn on the segment and try to trace it.
Wow. Wow. Wow.
Okay? So you continue to play with this. Right? Now, but basically, I use very simple expressions. Do you notice that? All right? However, we can also talk about what this symbol means. All right? Instead of just saying that there's a put on the calculation to do a lot of manipulation, right? Now you visualize it. All right? And then think about how it can be explained, right, by the definitions of sine and cosine. All right? Because we're using the basic definition for the sine and cosine in the unit circle. Right. So that's why I say I'm doing things on the unit circle and make use of it to discuss the properties or the basic definition or get familiar with the new trigonometric definitions. Right? Alright, so you can remove the trace just by dragging it, okay? But sometimes I think you can use the, let me see whether I can find the photos. Oh yeah. Now actually, I just let you know, the proper way of removing the trace is actually to use the refresh wheels, okay? But actually I just zoom in and out and they're already gone. Okay? But the proper way, I mean the more official way of removing the trace is actually to refresh. Okay? Understand? It can be found under the wheel sections of the toolbar. Okay? The menu. Okay, but anyway, I don't use it. Just let it go. You can continue to try. What else we can make? How about sine? Now this will be more complicated, maybe. Cosine alpha. Okay, now let's see the difference. If I multiply by 2 here, it's also a very good comparison. Right? So it's not 2 alpha, 2 times cosine alpha, 2 sine alpha. Where should be the point? Yeah. Can you see that? Now the trace may not be very interesting, but at least you know what happened. Okay?
Wow.
Okay? But my point is that we have to distinguish, right, what this expression means. I will make an adjustment like this. Or it can be if you like to do a more complicated one, just 2 cosine alpha, but keep the sine alpha. Okay. Now you can just look at the point first. You see the point? Does it make sense? Does it make sense? Okay. Only the cosine alpha is being multiplied by 2. Or in this case, only the x coordinates are being multiplied by 2, but not the y coordinate. Okay? Okay, so you can try to check it.
Ellipse?
Yes, it should be an ellipse, actually. I mean, the curve described by D should be an ellipse, right? The segment is just to create some emphasis or some highlights on the relations, or use it to create some pattern, a geometric pattern. Right. Now, finally, this is more challenging one. How about cosine square? Now you can't write in the usual way, okay? I mean cosine square, you still have to make. I think you have to put it here. Okay, cosine square. Square of cosine beta. Now, but be careful. This is not the usual way you write it. I hope it's correct. Okay, put it this way. Have I done it? Okay, yeah.
Let's convert it to the.
Oh, sorry. I make change to the point C. You're right. It's also convection. Interestingly. Can I do it this way instead? Let me see. Okay. Let's see how. No, but that may be just a shortcut. Okay. Oh, there's still a 7. It's quite strange. Right? So they still have 7 cosine square, sine square. Maybe they just modify the code, right, to let it accept this. But I think it's not the formal one. All right, what would it look like?
Huh?
Do you know why?
You cannot connect it as a square. Right? Do you know why it's like this?
No.
Anyway, analyze it carefully. Maybe. So if I use the arrow key, then it will remove. So you can create it yourself. Now, try to look carefully. I'm using the arrow key of the keyboard to change the angle, okay? That's why you see it changed by 5 degrees, I think. Here. I'm using the arrow key. Okay? But if you drag it, maybe you still can't guarantee you can change it by 1 degree each time. Because sometimes you can skip some of the value, right? So this is how you skip it, drag it. Okay? Okay, so you can continue playing with this, all right?
Okay.
Yeah. So my point is, just based on the simple definition, so you can make a lot of different things to try and explore, all right? So I can save this. Maybe I can save this file first. Maybe I save this file first.
对学生来说已经会觉得还好了，已经很爽。他说能动就很爽。你不还是我？
Okay, now I go on to talk about some other construction, right, based on the unit circle. Sorry, I forgot one point. We can first do the graph of sine and cosine. Because this is, now first of all, this is a unit circle. we are talking about the definition of sine and cosine based on the unit circle. Particularly, these two values at the same time is used to describe the point. Okay, this is the described point of the unit circle. But to look at the graph of individual function, it is another representation. Okay, so usually it can be done. You can, of course, you can put it on the same graph. Some teachers would like to put it on the same graph. That means the sine curve. I think probably you see it in the textbook quite often. Am I right? Yeah. But here, I can also choose it to put it in another graphic window, right, to let you know how the GeoGebra can handle it. That means instead of just putting it exactly on the same graph, I can now turn on this. Can you remember the wheel? Yeah. You can choose more than one graphic wheel. Okay? Oh. It's called graphic tool. Right? So I have another graph now. Yeah. Oh, it depends whether you want to line up or not, it's up to you. But I want to emphasize that this is another graph. Do you know what I mean? The points on the unit circle is another graph, which I extract information to display in another graph paper. Okay? Now,
you can decide the graph of sine.
Yes, you can. So how you can draw sine in this way? What I need is actually just the point alpha. Okay? Remember, alpha is the independent variable. Okay? And I want to draw the sine alpha. That means I want to describe the change of sine alpha depending on alpha. I need a new point. Okay? So I can press enter. And the point is here, the point E. Okay. Now, so let me see the point. This is the new point E. Can you see this?
Yeah.
Right? The point E is displayed on this side. Now, it's a bit tricky. I can do it because before I input it, I press this window. Okay. Otherwise, it may be still on this window. Okay. But don't worry, you can still modify the point E setting. All right. Because in the setting, in the advanced tab, you can see the point is actually displayed in graphic 2 and the algebra view. That means it is shown here. And it is also shown in the graphic view. Okay? So actually, now while you see the algebra window, in fact, you can take away some unnecessary objects if you want to make it simpler. Right? Sometimes you can check it later and then save your file before showing it in the classroom. The more important is that the same objects can be displayed in either or both windows, graphic 1 and graphic 2. Understand? You can adjust it anytime you like. And the consequence is that now if you turn to change alpha, you see E moving in another point. So I can hide this one first. So where's the point? Where's the point? Oh, okay, this one is not so high. Or maybe I just delete it. All right, can you see this? Now, I would like to do so because in this way, I can emphasize that the sine function is actually another graph. Okay, to describe basically how the sine alpha change with alpha. You understand? Right? So in fact, I would like to highlight this, although I can still put it in the same graph, okay? But I don't know how far the student understand the meaning if I put it together in one graph. Sometimes you may have, you still want to do it, or maybe the textbook still display it this way. Right? It's up to you, of course. Right? I think this year put it in one graph, but sometimes you have to think about it. What's the meaning or the purpose of doing it? All right? So unit circle is one picture here. But the graph of sine and cosine is another picture, right? That you can demonstrate on another. Because now we concentrate on seeing how the sine value change. Where's the sine? Where's the point? Here. Oh, I have deleted the point C. Okay, never mind. I can put it back. Okay. Do I need brackets? Let me check. how it works without the bracket. Okay, it's more proper now. So can you see the point C? The point C is on circle. Point E describes the change, right, of sine alpha, right, the sine theta. Can you get it first of all?
Yes.
Okay. Now, if you want to distinguish the two graphs, there's something else that you can try. You can change the color. Okay. If you now let me do it again. If you open this dial bar and turn on the gear, okay, you can see the grid or the axis. Let me check it here. The background, yeah, the background, the graph background can be chosen here. Can you see this? Can you see this? All right. And then you can turn on the grid. The grid here, you can show the grid. This is the usual one. And then you look like the usual graph paper. Oh. Okay. So you look like that. You're collecting the data and then put it back in the graph paper, right? To see how it looks like. Right? Or if you don't want the grid on this side, you can turn it off. Perhaps you also turn it off. Okay. You see that? And then now maybe you want to trace. Now there's a different way to show the graph. I only show the point on now, okay? But I can show the graph by doing the trace here. Turn on the trace. Can you see this?
Yes.
This is one way of doing it. Okay? And also note that the variable is now turned into gradient, or by default it's displayed in gradient. Because alpha, actually the underlying calculation is based on gradient. Right? Although it may temporarily display as an angle, you can choose to display it as a degree, angle in degree. Okay? However, all the calculation is done in gradient. I found that if you just plot the value, then it only shows the gradient. Right? If you really want to do the degree, you need a little bit more adjustment, right? Which is a bit more complicated. I'll show you later. Right? But just let you know, the first, I think the simplest way is to display the variable in gradient. Okay? But at least you know the basic idea, am I right? Okay? So you can see the graph here. Now this is what I call the trace of the point E. But if you want to see the curve, another option is to display the locus. Okay? So the locus is somewhere here, I think. Locus, right? The locus command. Okay? So the locus will give you the curve, right? Based on the movable point. Okay? So if I choose the locus, can you see the keys here? Select the locus point, then the point on object or slider. Okay? Because the point E is relying on the slider, alpha. You can also say that it relies on the point C. Sorry, is it true? Oh, no, it's not relying on C, it's relying on alpha. Okay? So I have to choose point E and the slider, and then to produce the locus. Okay? So I choose the locus too. Locus of the point E based on the slider. Okay? Now don't worry, it's now shown in the wrong window, and you can adjust it. Remember where? Advanced tab. Show it on the graphic 2, not the graphic 1. Then you will see it here. Understand? In that case, you have the locus. Understand? Now this is not a trace, this is the locus of the point E. Okay? Depending on the free variable alpha. Huh?
Only move the locus from the left to the right.
Right, you can choose the object, or here, open the setting.
Oh, setting.
Setting, yeah. Advanced tab, and then scroll down to find where to show. So that is the major features I want to demonstrate using the classic version, because the new version does not allow you to open the two windows at the same time. Okay? But I think that this option should be very useful in many different ways. Do you have any questions? Right, now you see only the range, right, from 0 to 2 pi. Right? How can you extend it?
By changing the alpha.
Yes, you're right. You can change the alpha because all this starts from the slider. Okay, so you can go on to do the setting and choose the slider. Can you see this option? It need not be confined to one cycle. It can be 0 degree, 20 degree, or even from negative 360 maybe. Okay, it can be. Now you can see the increment is 5 degrees. That's why when I use the arrow key to change it, it increased by 5 degrees. Okay, but you can adjust it later if you like. Right? So once you enter it, okay, then you go back to the slider. But now you start with you check carefully. It moves more than once around the circle. Right? And you can also see the locus this way. Have you created the locus? It's here.
我这个还可以更懂，那已经有定义的问题。
那 A 是怎么定义的？
你看我们这个删掉。你现在不是给我点这块去啊？
No, it is still in radian, but it's more than 2 pi. It's 4 pi now. I will tell you how to show degree. It's now still in radian. So 720 means 4 pi. Now you can change the range of how to range of how to have you changed it?
Yes, slider is cheap.
Oh, change. Oh, of course the minimum is still 0. Right? Change to
改一个 alpha 范围。
这个，然后是 A。slider 这个，这个，出来了，然后了解这个。
Can you find it? No, you have to get back to it. Slider.
你不要 graph one 对吧？
对，不要选择在
然后呢，在你就把就画格子，你再来点右边，哎，然后setting，然后给到对，所以我需要。
Slider. No, it's the corner.
哦，
Why I can't select the slider?
好了，然后对，
Will you select the slider?
你都已经做到这儿了。
那你那个格子呢？哦，这儿，
都出来了。
哦，那好深。
哦，那也就是点出来第选择一个喜欢的。
你看了我们
Minimize it because there's not much space on the screen.
所以我都
This is half the time.
那现在真的有点早。
是，
对啊，我觉得一般都过完了。
Okay, now it's the up. Now this one. We shall have to make changes here.
那我就做的。
Have to change here.
他语音这个已经在投了，他没有吧？我是11中，昨天他不是也是招兵
11中学那个，不是说那个那个非常奇，它叫 independent school，对啊，是 private， 他们
那有区别吗？
就是私立的呗，
不是
说那个国立，
是国立的，
国立
什么叫国立？
国家让你去探索未来需要出路，就这样。青岛
不是公立的，不是私立的，是国立的。
青岛那个太不容易了。
但他那个毕业出来，他能升大学吗？他能背过
Okay,
这
some
个
go
吗？
wrong with one.
他可以。
Can you change the slider? Can you change the range?
你不想做老师，你想去上课。
Maybe you try the files again later. I don't know what's wrong
在
with
哪里啊
that file.
在哪里？
Right, can you do this? Any questions about this file? Now, so that is the drawing of the functions, right, of the sine curve in radian, right? And now let's try to turn to degree, okay? Now for this graph here, I think let's check it. Yes, in the graphing window. Yes, I think if you look at the graphing, okay, the graphing wheel or the algebra wheel, the angles are displayed in degree, but it's only displayed in degree, right? Its value is still in radian. You can already see this, right, when you graph it. So it's a bit tricky. Let's say if you really want to plot the point alpha, but the values in degree, the only way I can do it is to divide it by 1 degree. Can you get it?
Yeah.
Divide alpha by 1 degree. Alpha is still the radian. Right? And divided by 1 degree, actually 1 degree will turn into a radian. And the ratio will give you the value in degree. Okay? Now you don't have to explain to the student. Okay? It is only the trace that we need to give the graph. Okay? So the value of E, if you look at it now, if you look at the values now, if you look at the values, okay, then you can see it on this graph, but I have to adjust the scale as well. Now, of course, now I think it should be fine because the scale, you see that, right? It shows only the very small part. It is a degree, and it all go to 360. So at the same time, you have to modify the graph, okay? The graph area. Now we have to turn on the x-axis, and then can you see the range? No. Oh, no, basic. Okay, yeah, basic one. Sorry, basic dimensions. The x-axis. Okay, I think you better start with negative 30 degree. You don't have to type degrees. All right, just change the numbers. So up to, let's say 720 or 750. Up to you. It's up to you. You can see it now. Right? So that is the first step. We try to display the graph. And the point E, you can see the point E, the value here. Can you see the value?
Show again how to choose the axis, the range of axis.
Yes. So the axis, now you open the style bar and you click on the gear, and okay, the first, actually you can see that these, can you see these two icons? One for each graphic window. Okay. So I'm chosen the graphic 2.
Oh.
Right? And under the dimension, the basic dimension, this is the range of x. Actually, you can also change the value of y. Right? If you don't need so large a range, that's enough, perhaps. Okay, do you see it?
Yeah.
Right? So you can change the range here, just turn on the number, a larger number, and at the same time, the coordinates of E is now displayed in terms of degree, just because I do the calculation here, all right, to make it turn into the degree, right, values. But there's no simple way, as far as I know so far. Okay? There's no simple way to turn it into a degree option, okay, in the graph, while in the graph in the requirements. Yes?
Just wondering, if you do any input, if we use the letter pi, does it recognize it as a 3.14? Or we have to decide pi first?
No, they know the pi value, right? Okay. And the symbol pi by default will go to 3.14. It's already set up here. Okay. All right, now finally on the axis or the grid, can you see the grid here? Yeah, I think for the x-axis, you can choose. You can choose the unit to be degree. Okay? And you can also choose the distance of the tabs, maybe 30 or 90 if you like. Let's see if it's better. Okay. Now this will show the mark on the x-axis. So you can always do this adjustment, actually, right? So it will give you the mark on the text and also use the degree symbol. Right? Now the unit here actually is just a label. Right? It does not turn or change your calculations. Okay? It's just a mark here on the screen. So if you now close the tab, I think this is not displayed properly. I don't know why. So I have to manually change the axis. Okay, it's still fine, I think. Okay, now so the x-axis here shows 90 degrees. It's much better to read. Right? It will be much better to read than this. Am I right? Is it okay? Alright, now I think I have to move on, right? So I save this file again. Right, so now I save another file, even though it's a previous one, but I save it as a new file, I think. Okay, now, so to record this. Right. Now I turn off the graphic tool for the time being, okay, to go back to focus on the unit circle. Now I have already saved this version as another file, okay, so I'm not going to work on this as a first file. So I just continue to do it, okay, because I already saved the earlier version. All right, I just now turn off temporarily the graphic tool wheels, okay. So I now go back to the unit circle. Now let me show you quickly other ways to create locus, all right, because you should know that this is the general ideas of doing things in the GeoGebra or the geometry window. For example, if I choose any line on the axis, I can create a movable segment. Can you see this? This is movable segment, okay? Okay, axis. If I now create a midpoint, now create the midpoint of this segment. Okay. How would the midpoint F change according to the segment? Do you know? What will happen if you trace the point F? What will you see? Any idea?
Ellipse.
Ellipse, you can have a try, or you know how to turn on the trace, right? Now I skip the step, right? I think you know how to turn on the trace, okay? What I want to show you is the locus, right? So if I now turn on the usual locus tool here, the locus, I want the locus of the point F, depending on the slider, or any another object. It can be another independent object you like, okay? So here, all right, so not really an ellipse, it's just another circle.
Wow.
Right. Now, so there's a general way to produce locus, okay? So locus can be created this way, or if you now move the point D, so what happens to the locus? Oh yeah, you can still adjust. But it should move continuously, I assume. It's a bit strange. Okay. We can continue to explore. I think I skipped this part, right? You can find out what should be the size of this surface, and where do you think this surface should be. All right. So you can talk about or investigate this locus. here I just demonstrate the ideas of locus. Okay? Now, or maybe I make another quick demonstration. All right, I put another quick demonstration. Now this time, I make a segment here, somewhere here, outside, okay, and I can drag any one of the point. Can you see this? Okay, and now I create 2 points. Oh, sorry, I cannot do it this way. Okay. No, because it's not. It's another question. Sorry. Okay. So maybe I delete this one. Sorry, I skipped that example. Right? I think that's a small step I have to demonstrate. Okay. So, but I still hope that I can show you some basic idea of producing the locus. Am I right? Okay. Now I turn to now this time I really turn to a modeling problem, right? To discuss with you. Now, if you want to find out the details, you can go to the book, the Oxford textbook. This one. Maybe this one. This one I extract from the AI. Okay. The AI standard levels textbook. You can see the page there. I think it's page. Where is it? Page 514. Okay. So they talk about trigonometry and then some modeling problem. Can you see this picture? Right, so that is a change of the point P, and then the segment also varies. And this is a point on the x-axis. Okay. And the book here discuss, okay, the locus, what should it be, how should it vary. Actually, you can also refer to the GeoGebra book I recommended last time. This is the GeoGebra book talking about modeling, okay? Mathematical modeling. You can find this book. Right? And turn to page 337, the locomotive. Can you see the part here?
Yes.
They call it piston, okay? When you wheel turn, this piston, okay, will also move horizontally, right? I don't know whether you still recognize, okay, this kind of mechanical part, right? So this somehow this part of the book also talk about this problem, okay? And then you can see some detail. Also, this is the graph. Now this is graph I'd like to show you how to draw, okay? So this red segment is fixed in length. It's not the same as the previous drawing I showed you, right? Because when I turn this one, this point will also move horizontally, right? Because this length is fixed. Can you imagine? This is like a piston, right, in the locomotive. Okay? So what would it look like? How to draw it? Now I go back to the GeoGebra file. Okay. So when I turn the point on the circle, okay, I need a segment here, all right, with a particular length. Now this has to be done in an indirect way. I have to use the circle, another circle tool, right, depending on the center and the fixed radius. The radius have to be input as a number. Understand? Understand the tool here? Okay. So if I choose it, then I have to check this point as a center and then input the radius. Now, of course, to make it reasonable, I think the radius should be bigger than 1, right, or even bigger than 2, right, so that it will be not falling inside the circle. Okay? You can choose anything you like. I choose 3. Okay. So if you move the point, can you see that? This is a circle of a fixed radius. Okay? And what I need is the intersection of the circle and the x-axis. While doing so, I can create a segment of fixed length. Can you see it? So now it's running like a wheel. Understand?
Yes.
So the center is C. Radius is constant, 3. All right, and I mark the intersection of the circle and x-axis. And when I join it, this length is always 3. Always equal to 3 units in length. Can you get it? Can you follow? Can you do it? So what we'd like to ask is that how do you expect the point D move along the x-axis if you turn the point C on the circle? All right. So we'll record the x-coordinates of D, right, to indicate the length, of course, from a particular reference point. Okay. Let's see we measure it from O, right, and then let's see how the x-coordinates of D varies as the point C move on the circle. Understand? So similar to last, now I can close, I can hide the circle because this is not really needed. I don't need to show it. Okay. So you can imagine, it's going this way. Can you see this? Okay. So we are now going to record the value. Okay. Okay. So how do you record the value? Now I need to go back to the graphing tools. Now the graphing tool. You understand? This graphing tool, okay, to draw the point. I don't need this point now. I don't need this graph. Okay, I want a new graph. Can you see the various part? So what should be the point I should input here? It still depends on alpha. Right? It still depends on alpha angle. And if you want to keep it in degree, then you have to do it this way. Can you remember? Divided by 1 degree. Right? A little tricky. And the value so I want to record is simply the x-coordinate of the point. What's the name of the point? X-coordinates of, is it F? I don't know.
For me, it's E.
Let's try. D. Okay, no worry. We'll just change it. Okay, so the point G, I should display it in the second window. It's right now, right in the second window. Okay, can you see it?
Yes.
No, this is not the point. This is the original graph. So where's the point? You can't see it in this range.
Oh.
Remember? It's here. Okay? This way. Okay, now I also like to make the locus, right? Why I can't get it? Can you do the locus? Okay, yes, you can see it now. All right, can you see it?
Yes.
So this is the locus. And maybe I don't need this graphing window, or algebra window. So I can enlarge a little bit here. Okay. can also make circle clear. Okay, just to make it easier to read. If you right-click the slider, then you can drag it and move it. All right? I think it works now. You see? So what do you think is the function of this curve? So that is the question in your textbook. Okay? So once you have this graph, you just plot it point by point, okay? And then you can try to think about it. How would you describe this function, or so what should be the function, right, behind this curve? Right? So that is okay. It's left for you as investigation. All right. Understand? So you can refer to the book. You look at the book here. That is the question they ask. So they first collect some points. I skip this part, so I do not have this point, but I assume that you understand how the graph is generated. It's just based on the movement, and then you collect the point directly, but you don't know the function behind it, right? You don't see the formula or the function behind it. You only see the graph directly. Now this is the one type of modeling task, right? So you generate the data, and then you plot the point and graph. Even with the GeoGebra, you can plot it very accurately, right? But you still don't know the formula or any function behind, okay, the variables, all right? So as a modeling task, you may like to think about it, what should be or what could be, okay, any kind of function, or is it easy to find? Something like that, okay? And then you can try to work on this. And so further down the question, they ask, what do you think is the curve? Someone suggests cosine. So no, you're using the cosine rule, okay? Or some may assume that it may be a cosine function. So just investigate a sinusoidal model for the data. Right? But it turns out to be not a simple trigonometric function at all. Okay? So you can have a try later on. Is it okay? Right, so this is safe. So the engine is called a piston, the movable part of the rail, the car. Okay, so this is at least one possible modeling type of questions that you may want to show and discuss with the student here in this environment. Do you have any questions? Now, of course, you may not directly know what extent this function is, but it's still good to have a try while fitting a cosine curve. Okay, with the given information here, you may wonder, can we input a cosine curve, and then to see how far it fits the data. Okay.
C 你是半径很大的圆，然后圆跟 x 就作为连接 C T。对啊。C T 是半径分出的线嘛。
C T 是圆的半径。
对，半径可能是不会变的。
这个 C 对圆是不动，这个
圆心会动，但是半径不会动。半径不会动。对。
X 随便找个点就可以连上，是吧？
可以随便找，就一个角点，随便找。
圆会动啊。
对啊，那是。
一个点。
那你连接 C T， 连接 C T 就可以了。因为你要看。
Okay, now I think I will do one more example, okay, to further continue to demonstrate the use of this kind of multiple graphic wheels, okay, and how to make use of it. So okay, now I close this one. I already saved several files here already, okay. And I'll show you the links later, okay, of my file. Here, the last one also using GeoGebra graphic classic, right, the classic wheel. And now let's turn to the let's see, how to start with. Okay, I start with the graphic wheels again. Just a simple graphic wheel. Okay. Now I'm going to make a cone of a fixed volume, right? But for the beginning, we are just freely make a general cone, okay? And then study the change of this volume according to certain conditions. Okay? And to start with, I use a simple setup here. Okay. Now A is the point, okay, at the origin, because I just click directly at the origin, so A is fixed, and B is movable. Can you see that? And I have a segment AB, all right? Can you see it? And then I can create a point here on the y-axis, okay, which is perpendicular to the axis and through the point B. Okay. Now I can use the ordinary perpendicular line construction, okay, but I can also show you another simple way because I would put it on the y-axis, so the y-coordinate, so the x-coordinate should be 0, okay, and the y-coordinate is just the y-coordinates of the point B. Okay. So this is done algebraically, okay, just to input the y, the points here, C, then you can see the point C. Understand? Okay. Now, so this will be the basic structures of the cone, because that will be one of the slant edge. If you revolve it around the x-axis, y-axis, then you have a cone. Okay? And the C will be the center of the base. Okay? I'm not talking about the inverted cone, okay? Because I'm imagining a cone that can be used to hold water, so like a cup. Something like that. Okay? Now, how to create a cone? I don't need the algebra wheel. I can close it. Okay? Now you can see only this simple line segment on the y-axis. Okay? So here I can turn on the 3D graphic wheel. Can you see it? Okay. Now you will find that actually in the 3D graphic wheel, you also see the point A, B, and C. It is exactly the same plane that you see here. If you move the point, right? So actually, if you click on the point and any one of this object, and then think about, look at this, the point P, for example, the point P is appearing in the graphic wheels and also the 3D graphic wheels, right? But you can turn it off if you like. Okay. So this is the 3D graphic wheel. Okay. And I want to use it to produce a cone. Now how I can make a cone? You can check it here. I think that is the cone. Okay. You select the bottom point and then the top point, and then enter the, let's check it again. Enter the radius. Can you get it? Okay. Now the radius, so what should be the radius? The radius would be simply BC. Okay? So top point and then the bottom point here means the point C. Okay, maybe I need another variable. So I forgot to, let's say I want to add. Oh yes, Because I choose the x-axis, I remember, because I choose the axis as the reference, so the radius of the cone will be simply the x-coordinate of P. Yes, you can see that? Okay? So I think it will make the construction simpler. Okay, so now I start using the cone tool, the cone drawing tool. Click the vertex and then the base center, and then now the radius, which is x-coordinates of P. Oh, sorry, I turned it around. Okay, I just do it again. Okay, from this point to this point, and then this one will be. Is it right? Okay, good. So you can now drag it this way, and then.
So is it the same if you click on the 2D version, on the 2D point A and C?
Yes, we can do it. You are right. They can be done. I can see that it's still vary. But why I can't just change it to? Okay, maybe I'll just leave it this way. Okay. Now this is the. If you add some segment here, you can highlight it. Can you see the segment? I draw here, but it also appears on the screen. Okay, so you can see now the height and the radius of the cone is just controlled by the x coordinates of x and y coordinates of P. Okay. And now I want to do something. Okay. Now you can see that the cone is freely movable, right? I can change arbitrarily. Now I'm thinking of a particular volume, a cone of particular volume, right? So if I assume that the volume is changed, is constant, then how would the radius and the height, okay, relate to each other? Can you imagine? So maybe I put it this way. Okay, now I open the algebra view again to do some calculation. Okay. So I don't need this one. So I suppose I want the volume of the cone to be, let's say 100. I don't know how big it is. Let's try. Okay, 100 cubic units. Okay, and then so in what way the radius and the height will be related according to this? So suppose x is the radius, right? The radius of the cone, okay. So that means the y will be the height of the cone, okay. In this graph, how would x and y be related? So you know that 1/3, okay, x squared times y will be equal to v, the volume, okay. So in this case, I just put down v divided by, or 3v divided by x squared. Would this formula give the values of the height? I need also pi, okay? Yeah. You talk about the pi. Let's try it here. I just put pi, and you show already the pi. The pi symbol.
Very smart.
Why they changed interesting. Why they change? Oh, I see. They display the function. P is the function name. Okay. P of x is function name. Doesn't matter anyway. I think you know what it means. Okay, so 100. Now you see that 100. By the way, V is now another slider. Okay. And you can also change it. Of course, it doesn't make sense to have negative value. You can change it up to 200. You can change it by values of 10. Can you see the graph? And I can also display the slider here on the screen. Okay. So I now close it. So this is what it means. This graph shows how the height and the radius should be related. If you assume the volume is set to be a particular value, let's say 60. Understand that? Okay. That means if I put the point here, the volume of the cone should be 60. Can you follow? If I put the point B here, the volume of the cone should be 60 now. It is a fixed volume. Right? Now, can you guess, under this condition, if the volume is fixed, okay, how would the surface area of the cone change? How will the surface areas of the cone vary? Well, we need another calculation, perhaps. All right? So we need to open the algebra view again. So what's the surface area? The surface area S, maybe you can also call it S of X, okay? It depends on the radius. And so the curve, I just call, to make it simple, I just look at the curve surface area, all right? It is pi times, what is it, the radius? Pi r L
squared plus.
So pi r L. L is the slant height, okay?
That's right.
Yeah, which is actually this length, AB. Okay? So AB depends on what? Depends on x, and then also this vertical value. Right? Now, if all depends on x, then it would be something like that. It would be
X over cosine. I know.
no. You can do it. You can do it this way. First of all, square root of x squared plus. If you want to make it more general, okay, it's in this graph it is just the y coordinates of p. Okay, understand? So that's what we do. This is the surface area. That's the base. So in this way, I can check how the surface area. Now it does not show the values now, okay? But you can ask to. I can show the values of surface area in another graph very soon, okay? But you can now imagine if I move the point B along this graph, this curve, and you will see the change of the cone, and then correspondingly the surface area will also change. All right, understand? All right, now in order to demonstrate, to show the point, then I put it on the graph again. All right, I just put the point first. The point I like is the point X, and then the surface area. Or I don't need to, I think maybe, because I have already the function, I think they will show the functions directly. Maybe I skip this part. Okay? What I need to show is to show the function. But where is the function S? It's not shown yet. Or it may be here. Do you see the blue line? Yes. It is the function S. Okay? But of course you can't see the whole picture clearly. Okay? Okay, now the last part is to open the graphic tool. Okay? So in the graphic tool, I think I can move it around. I don't know. This is the graphic tool, and this graph I want it to be shown in the graphic tool, not the graphic one, so I close it. Also not the 3D graph. Okay? So I show it now. And how can I see the whole picture? Did I make anything wrong here? Let me check. So it does not look like the one I expect. What's wrong? Let's go back to this one. Ah, I noticed that. Okay, I think I forgot to adjust it because I want the surface area to be really depending on the movable one B. Okay, it's not the general variable, so I make a mistake here. Actually, I want this. When I type it again, I want this to be the x values of B times the square root. Okay, based on the x values of B, which is the radius, and then also the y values of B, the height. Okay, in this way. Alright, can you see it? So S is now the value based on this one. Okay, and let's see how it looks like now. But it does not depend on x. In that case. Okay, because I'm not making the B changing. Okay, now the final step, I want to stick the point B. Let's see whether it will make it change. Okay. I stick the point B on the graph. So that's a function. I can attach the point B on the graph. Okay, I'll do it again. Okay. All right. So the final part, I still can't manage the graph on the right. Okay, let me see. What should I plot here? Maybe I should plot. So I should plot the point S. So I don't need the function actually. So I don't need to call it a function because it just depends on the. Why we still call it a function? It's quite strange.
My is a number.
Huh?
My S is a number. It's not.
So what's the definition here? So I don't treat it as a function directly. This one is more complicated. Sorry. Okay, the square root of x coordinates of b squared plus y coordinate of b also square. Oh, it's still a function. So why it does not change? Maybe I just, oh, sorry. I try another label to see whether it makes sense. Yeah, about this, I delete it. All right, I try to, okay, try last time, see whether it works or not. I call it SU, surface area. Okay. Yes, now it changed. Okay, this surface area changed according to the point P. I don't know what's wrong with the previous labeling. Okay, but I think it works now. But on the graph on the right, I just now want to plot the point x, and then SU stand for surface area. Can I see the point? No. Where's the point here? Have I input the point? What? No. It's missing. So, another interesting thing, why the point is not shown? I should be able to plot this point. Okay, one more time. I hope it works. No, still can't. Okay, maybe I do it this way. Okay, one more file. So maybe I just directly enter the values, which is the oh, the point is still missing. I see. Okay. All right. So I think I have to stop here. Maybe that I can't still figure out the problem for this case. I'll try to fix it. If I have a solution, I'll tell you later. Okay. So what I want to do is that I hope that this graph will show the surface area variance with the radius. Okay. So if the radius change, then how will the surface areas also varies? Okay. In order to see when will the surface area be the minimum. All right. So that. By the way, why I do so? Because I want to show how the three windows can be used at the same time. Right? This is the 3D objects. This is the constraint. Okay? Knowing how the radius and h are really related. And then at the end, I also studied the surface area in another graph, right? So they can be demonstrated. I tried before, but somehow I forgot some of the, maybe the minor step of doing it. Actually, it's here. Yes, I think it's this one. Okay, this one. So the outcome should be like that. You see the graph? Okay. So originally I want to study so how the surface area relate to the radius. If the volume is fixed, okay, and this can be another graph that I can generate. So it is another way to visualize, right? The changes among the perimeter. So theoretically, you can use quite a number of windows at the same time, all right, in order to study more complicated relationships. So maybe I'll check again what should be the step of doing it, and then share with you next time. Okay? So I think we better stop here. Right? Some of you have to attend the evening session pretty soon. Okay? So we stop here. Okay. Okay. See you tomorrow. Right?
没有，毕竟我就是我应该先画的函数要取点。对，你先画那个 UPX，然后就取点。